Hello, this session will cover finding zeros of a polynomial function, and this video is intended for the class NCBM 0114, which is a co-requisite with Math 1314 Pre-Calculus 1. The rational zero theorem is something that you will see, I believe, in section 2.5 of your college course, and it is a theorem that helps us, just like the name says, to find any rational zeros. Remember, zeros are those x values for which the y is equal to 0. So we're still finding those x values. We also refer to those as roots or solutions. And the word rational implies that those numbers, those x values, will be rational numbers. And so a rational number is the ratio of two integers. Just like we had rational functions, they're the ratio of two polynomials. Rational numbers are the ratio of two integers. So here we can have numbers like integers themselves, like 2/1. They could also be negative, let's say -3. If it doesn't have a denominator, we know it's a 1. So those are rational numbers. Also, let's say 0.333. That is also rational because it could be converted into a fraction, and it is in fact 1/3. What if we have something like 0.25? Well, 0.25 could be 25 hundredths, so that makes it be a rational number. And it also could be 1/4 if we simplify the fraction. So of course, some decimals could be turned into fractions, therefore they're rational. Others cannot. And for example, the most famous irrational number could be pi. The second most famous will be e, which is also irrational. And anything that contains a square root, for example, the square root of 2, that does not have an exact answer, then we could also consider it irrational. So all of these numbers will not be part of this theorem. Condition is that they have to be turned into a fraction, like the examples that I've shown here. So what we are going to do is look at two things from your polynomial. We're going to look at the constant term, and we're going to look at the leading coefficient. And from there, we're going to make some combinations, and those are just going to be possibilities. It doesn't mean that all of those x values will be the solutions or the zeros of the polynomial. They're just going to be possibilities, but they're all going to be rational numbers. So let's get started. So right here, the first thing we need to do for example 1 is, well, it says use the rational zero theorem to list all possible rational zeros of, and we have a polynomial of degree 3 because that is the highest exponent. So the constant term is going to be -6, and the factors of -6, it could be 1, it could be 2, it could be 3, and it could also be 6. Well, we could also have -1, -2, -3, and -6. So sometimes, to be able to represent both the positive and the negative numbers, sometimes the book or your professor might refer to it as plus minus, oops, that's wrong, plus minus 1, plus minus 2, plus minus 3, plus minus 6. So that will be that will imply the same thing, that you have all those numbers positive and the same numbers negative. Now the leading coefficient, so this is a constant term, don't forget that. The leading coefficient is the number that goes with the variable that carries the highest exponent, because that will be the degree of the polynomial. So if you don't see a number, you know there is an implied 1 and positive. The only factors of 1 will be +1 and -1. And so we could say that with plus minus 1. I am not sure how you will enter your answer on WebAssign, so just make sure if they want you to if there's an option for a plus minus, or if you have to enter the positive and then the negative. So now what we're going to do is we're going to list all the possibilities that come from the constant term, so plus minus 1, plus minus 2, plus minus 3, and plus minus 6. Now this one is not going to be too difficult because we're only going to be dividing by the factors of the leading coefficient, so which is plus minus 1, and that's why we have this line here. We're actually going to be dividing. So the idea is that if this is a 1, once you divide the factors that I have in blue, plus minus 1 divided by 1, by this one here, it will just be 1. Plus minus 2 divided by 1, it will just be plus minus 2. And then plus minus 3 divided by plus minus 1, it will just be plus minus 3. And finally, plus minus 6 divided by plus minus 1, it will just be plus minus 6. So now all of this are the possible rational zeros of that polynomial. Now, how many possibilities do we have? If you are thinking 4, double that because we have the positive and the negative. So we have 8 possible rational zeros, counting the positives and the negatives. However, this is a polynomial of degree 3. And because of that, we can have at most 3 zeros. So that doesn't mean that all of these numbers could be the zeros. They're just possibilities. So now let's work with example 2. And we're going to list, again, the constant factor, the constant term, which is -3. Factors of -3 will be plus minus 1 and plus minus 3. Remember that implies that you have positive 1, positive 3, -1, and -3. Now the leading coefficient, now it is a 4, like we have here, positive 4. And so the factors of 4, we will have plus minus 1, plus minus 2, and also plus minus 4. And just remember that implies that you could have positive 1, positive 2, positive 4, but also negatives, -1, -2, and -4. So now to list the possible rational zeros, of course, we need to write down the factors of the constant term, just like we did before. And those are right here, plus minus 1 and plus minus 3. Now we're going to be dividing by the factors of the leading coefficient, 4, and those are listed here. Plus minus 1, plus minus 2, and plus minus 4. So now to continue this problem, now we're going to have more combinations. So first we take the factors of the constant and we divide those by 1. So they will be the same, plus minus 1 and plus minus 3 integers. Now we're going to take the same factors of the constant and now we're going to divide them by 2. So we're going to leave them expressed as fractions. 1 divided by 2 and 3 divided by 2. So we have plus minus 1/2 and plus minus 3/2. Now we have to do the same with the 4. So we're going to take 1 and 3, divide by 4. So we get plus minus 1/4, plus minus 3/4. And remember, we have to have the positive and the negative combination. So from here, we have many possibilities. We have 1, 2, 3, 4, 5, 6. And then if we count the negatives, we have a total of 12 possible rational zeros. Now, that doesn't mean we're going to have all of those being rational zeros because the degree of this polynomial is a 5, and that tells me that we could have at most 5 zeros. So now let's move on to the next page so we know what we do once we have all those possibilities listed. So here, finding zeros of a polynomial function. So to find a rational zero, we could use the trial and error process. Now, if you have several possibilities, it's kind of tedious, but you know how to do synthetic addition, and that is kind of easy for us to do. So that's the way we're gonna check. And remember, if we are testing a value, let's say that value is called C, and we're testing if this is in fact a zero of a polynomial, then if we take the C across the equal sign, instead of adding or having that invisible positive sign, it will be subtracting x minus C. And remember, that could be a factor. So the idea here is that if you can divide a polynomial by a factor, the remainder will be 0. And so if the remainder is a 0, that implies that if you substitute that x value, right now we're using the letter C to generalize it, it's just a number. If you substitute that x value, you will get a function value or a y value of 0. That's another reason we call them zeros. And how do we know that? Well, because by the remainder theorem, once you perform synthetic division or long division, if your remainder at the end is a 0, you could say that that is a factor of the polynomial. Well, actually, tracing back my steps, we could say that C is a solution, therefore x minus C is a factor. And if that occurs, then we know that it is a 0 of a polynomial. I know it sounds very repetitive, but it's all related. So that's how we're going to test. So if we get a remainder of 0, then we will consider that to be a solution or one of the zeros. So let's get started. And we have here the factors. We're going to need to list the factors of the constant term of -20. So we'll have plus minus 1, plus minus 2, plus minus 4, plus minus 5, plus minus 10, and also plus minus 20. Now, thankfully, we have a leading coefficient that is equal to a 1. And so that makes things easier because we will just be dividing by plus minus 1, which will actually allow us to say that our possibilities are just going to be the factors of the constant term, because we're just dividing by 1. So we'll have plus minus 1, plus minus 2, plus minus 4, plus minus 5, plus minus 10, and plus minus 20. So we have 1, 2, 3, 4, 5, 6. We have 12 possibilities. And so at this point, it could be a little overwhelming to graph, I'm sorry, not to graph, but to test for all of those. So if you are allowed to use a graphing calculator in your class, what I would strongly suggest is that you graph your polynomial, and you could graph it in your graphing calculator. You could graph it on Desmos if you're not taking a test, but of course this will depend on your instructor. If you are one of my students, I don't have a problem with that, and I call that making an educated guess with the help of a graph. So I'm going to try to use Desmos to graph it here. However, I'm not so sure that it will be recorded on the video. So while I'm graphing it, I would like for you to do the same. Use your graphing calculator or your cell phone. Go to Desmos if you need to, and just go ahead and try to graph the polynomial. So you will go to your graph section, y equals, and of course you will enter your polynomial x to the power 3 plus 8x squared, and then plus 11x minus 20. Okay, now on this graph, I could see clearly that the polynomial crosses the x-axis at x equals -4. That one is for sure. Also, I have, well, actually, I could see clearly as well that it crosses at +1. And so that's how I'm going to start testing. Now, I'm still going to do the work, but I have a good idea of where to start. Now, when you give fractions, sometimes they're not as clear, but so far I said -4, and I'm also going to test +1. So let's go ahead and do that. We're going to use synthetic division, of course. So first, we need to copy the coefficients of the polynomial. Remember, they have to be in descending order, so starting with the highest exponent. So for x cubed, we have 1. For x squared, we have +8. For x, we have +11, and for the constant term, we have a -20. Remember, if you're missing any terms, you have to keep up the space or save the space with a 0. Even if you're missing a constant term, you still need to put a 0 at the end. So I'm going to go ahead and test +1. So first step, drop the first number, 1, then multiply 1 times 1. Then we combine 8 plus 1 is 9. Then we multiply 1 times 9 is 9. 11 plus 9 is 20. And +20 times 1 gives me +20. Combine like terms, -20 plus 20 is 0. So because of our remainder is 0 by the remainder theorem, we could say that the x value, x equals 1, it's in fact one of our zeros. Now, this is actually a really nice trick that I want to teach you. So if you start with a polynomial of degree 3, you know this represents x squared, this represents x, and that is our constant term. So the resultant coefficients are representing x squared, x, and of course the numerical term, and they're all positive. So what I'm going to do is now I'm going to test for -4. But I'm going to make my life a little easier because I'm not going to start from the original coefficients. I'm actually going to use the new coefficients that I got here. So I'm going to say 1, 9, and 20. And so this is pretty convenient because you can save a lot of time. So we drop the first number, 1, multiply -4 times 1, that's -4. 9 plus -4 is 5. -4 times 5 is -20. 20 minus 20 is 0. And so now what I have is I have finished, and there's nothing else for me to test because Remember, we started with something of degree 3, then we went to degree 2. Now this is degree 1, and that's our constant term. So far, well, since the remainder here is a 0, we could also say that x equals -4 is in fact another 0. And we are missing one more. So what I'm going to do is go from a factor such as x plus 5. And what I'm going to do to find the 0 is I'm going to take that x plus 5 equal to 0 and then solve for x. So that will be x is equal to 1. And so that one right there will be my third solution, or root, or we also call it 0. Remember, that is the x value. So we have found all three of them, and that was -5. And we have it right here. Now, what else could we do with this? Well, we could say that this polynomial equation could also be written with the factors that I'm going to write down. So it could be that f of x could be written as x plus 5 from the 0 times x plus 4 from the 0, and finally x minus 1 from the 0. We also, if we know the zeros, we know the x-intercepts, and those will be the points 1, 0, -4, 0, and also -5, 0. If they're x-intercepts, the y value must be 0, and that's another reason we refer to those x values as zeros of the function. Okay, so we did the work of a third-degree polynomial, and we were able to see how the rational zero theorem allows us to rewrite such functions as products of a linear function and a quadratic factor. Find the zeros of the quadratic factor. Okay, we don't need to do this. We already went ahead and factored the whole thing. So what this statement is referring is that at the point where we found our first 0 was +1, we had this factor, x minus 1. And then the other factor was here, x squared plus 9x plus 20. Now, at this point, since you are supposed to be proficient at factoring, you could try to factor it. So it will be x, product of two binomials, x and x. The sign is positive, so that tells me both signs will be either both negative or both positive. But because this one is positive, they both have to be positive. Now, factors of 20, we have 1 and 20. We have 2 and 10. We have 4 and 5. They're all positive, and the only combination that gives me a +9 when I add them is 4 and 5. So that's what we use here. And see, if you have your factors, you could easily go from factors to zeros. So it will be x equals to 1, x equals to -4, and x equals to -5 by using the zero factor property. Now we're going to do one more in the last one, and this one says find all zeros of -2. So -2, we're going to list factors of the constant term, so that will be +(-1) and +(-2). Now the factors of the leading coefficient are just +(-1) and +(-2). So what that tells me is that all my possible, let's call it rational zeros, are going to be just +(-1) and +(-2). So we only have 4 possibilities. Let's try to test them all. So I'm going to start with +1. The coefficients of this polynomial, we have 1, 1, -5, and -2. So first step, again, we're going to use synthetic division with the hope to get a 0 here for the remainder. So we drop the first number, 1. 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. Negative 5 plus 2 is negative 3. 1 times negative 3 is negative 3. Negative 2 minus 3 is negative 5. So we could say that positive 1 is not a 0. Now, let's go ahead and try with negative 1 and see what we get. Okay, so now we're going to divide by negative 1. So first step is the same. We just drop the first term. Negative 1 times 1 is negative 1. 1 minus 1 is negative 1 times 0 is 0. Negative 5 plus 0 is negative 5. And negative 1 times negative 5 is positive 5. Negative 2 plus 5 is positive 3. So we could say that x equals 1 and x equals negative 1, both of them are not zeros. So now the next thing for us to test is going to be positive 2. Well, this is a polynomial of degree 3, and what that tells me is that we could have at most 3 zeros. So let's see what will happen here. If we try to test with positive 2, drop the 1. 2 times 1 is 2. 1 plus 2 is 3. 2 times 3 is 6. 6. Negative 5 plus 6 is 1. 2 times 1 is 2. Negative 2 plus 2 is 0. So we have found one of those, positive 2. This one is a 0. So now let's trace our steps back, and we started with something of degree 3, then x squared. Then this was the x, and this was our constant term. After dividing by the factor x minus 2 or with a 0, x equals 2, we got 1x squared plus 3x plus 1. Now, one thing we can do here is try to factor it, because so far we have that our function could be written this way. Now remember, if this is a 0, the factor will be x minus 2. The other factor is here, x squared plus 3x plus 1. And unfortunately here, there's nothing else we can do because this polynomial, this trinomial is not factorable. The only thing we could do at this point is use the quadratic formula. And so I'm going to do that quickly. So we have that a is equal to 1, b is equal to 3, and c is equal to 1. So I'm going to use the quadratic formula to find the remaining solutions or roots. So remember that is negative b plus minus square root of b squared minus 4ac, everything divided by 2a. So this will give me negative 3 plus minus square root of 3 squared minus 4 times 1 for a and c divided by 2 times 1. So by simplifying this, we'll get negative 3 plus minus the square root of 9 minus 4 divided by 2. This will be the same as negative 3 plus minus the square root of 5 divided by 2. Now from here, you need to consider that you have two solutions. One of them will be negative 3 plus the square root of 5 divided by 2, and the other one will be x equals negative 3 minus the square root of 5 divided by 2. Now, those two solutions could also be written this way. If we split the fraction, so negative 3 halves plus the square root of 5 over 2, and the other one will be x is equal to negative 3 halves minus the square root of 5 divided by 2. So now if we count them, we say third degree, we have 1, 2, and 3. Only one of them is rational, and the other two that contain the square root of 5 are irrational. So this concludes the video. Thank you for watching.